We conclude this chapter with a discussion of RC circuits. There are two types of RC circuits that we will consider: charging and discharging RC circuits. Both of these types of circuits will have one resistor and one capacitor that are connected in series. The charging RC circuit will have these two circuit elements connected to a battery as shown here. Let us say that the battery has an EMF or a voltage of E, and this battery will tend to push electric charges around through the circuit. If we assume that initially the capacitor is uncharged, then the battery will begin to deposit charges onto the capacitor plates. Initially, charges could freely flow onto the capacitor plates, but as time passes, charge will accumulate on these plates, and the charge that accumulates on the capacitor plates will oppose the addition of additional charges onto the capacitor. The purpose of the resistor is to slow this process down. For the typical values of battery voltage and capacitance that we use in physics lab, it might take on the order of microseconds for the voltage drop across a capacitor to be equal to the voltage of a battery. By placing a resistor in this circuit, we are inhibiting current from flowing around through our loop of wire. Because of this, charge will be deposited onto the capacitor plates at a slower rate, and we could have the time scale for charge to be accumulating on the capacitor plates to be on the order of seconds or tens of seconds instead of microseconds. As the charge is accumulating on the plates, the voltage drop across the capacitor will increase because Q equals CV, and in turn the current flowing through the resistor will decrease because V equals IR. We can apply Kirchhoff's loop law to this circuit, and when we do, we would have plus E for the voltage of the battery, minus Q over C, the voltage drop across the capacitor, and minus IR, the voltage drop across the resistor. When we return to our starting point, we set the total change in voltage to 0. When we solve this problem, we would look at the current and think of current as a delta Q over a delta T. And if we take the infinitesimal limit, we would write current as dQ dt. Then we would have a first order differential equation for Q that we can solve. Solving for the charge on the capacitor plates as a function of time, we would get an equation that looks like this. The charge on the capacitor plates at any time is equal to C times E, the capacitance of the capacitor times the voltage of the battery, times 1 minus E raised to the negative T over RC. The term R times C is sometimes referred to as the time constant of an RC circuit. Similarly, we could say the current that is flowing through this circuit is E over R times E raised to the negative T over RC. Look at these two equations and convince yourself that the maximum charge on the capacitor when the capacitor becomes fully charged is equal to C times E. One way you could think about the physics of RC circuits is to look at these equations for the charge present on the capacitor plates and the current flowing through the circuit, and ask yourself what these equations will look like at very early times when t is approximately 0, and what will these equations look like at very late times as t approaches infinity. The other type of RC circuit that we will consider is the discharging RC circuit. A discharging RC circuit will contain one resistor and one capacitor as shown here. The discharging RC circuit does not contain a battery. We will assume that initially at time t equals 0, the capacitor contains an amount of charge Q0 on its plates. So we imagine that we take a resistor and a capacitor that is already charged, and we connect these two circuit elements together as such. The moment we build this circuit, charges on the capacitor plates will repel each other because each capacitor plate has the same sign of charge on it, and the charges will now be able to flow to the other capacitor plate through the wires and the resistor. Initially, there will be a current flowing through this circuit, but as time proceeds, the current will fall away to 0. We could apply Kirchhoff's loop law again. The voltage drop across the resistor is IR, the voltage across the capacitor is Q over C, and keeping in mind the direction that the current is flowing through this circuit, We could find that Kirchhoff's loop law gives us the charge on the capacitor plates as a function of time, could be written as Q naught times E raised to the negative T over RC. And the voltage drop across the capacitor could be given as Q naught over C times E raised to the minus T over RC. The equations shown here give the charge on the capacitor plates and the voltage across the capacitor as a function of time. Because the discharging RC circuit contains only two circuit elements, one resistor and one capacitor, we could infer that the voltage drop across the resistor must be equal in magnitude to the voltage drop across the capacitor. Therefore, I could think of this equation for the voltage across the capacitor as also describing the voltage across the resistor. Because we assume that the resistance of the resistor is constant, I could then use Ohm's law, V equals IR, to find the current flowing through this circuit at any time. As a final comment, I want to explicitly mention that we are only able to set the voltage across the capacitor equal to the voltage across the resistor in magnitude because there are two circuit elements in the discharging RC circuit. In the charging RC circuit, where there are three circuit elements, we cannot set the voltage across the resistor equal to the voltage across the capacitor. We will now demonstrate an example RC circuit problem. Before proceeding, pause the video and, based on how the problem is written, decide if this is going to be an example of a charging or discharging RC circuit. This is an example of a discharging RC circuit problem. Let's think about what happens. Initially, the switch in this circuit is going to be placed in the horizontal position. So initially, the circuit will look like this. When the circuit looks like this, charge will flow from the battery and accumulate on the plates of the capacitor. Now, we could ask how much charge will accumulate on the plates of the capacitor after a very long time has passed. And that question will essentially be identical to asking how much charge will accumulate on the plates of a capacitor in this circuit, containing just a 9-volt battery and a 0.1 microfarad capacitor. Why are we not considering the resistor in this circuit? Well, after a very long time has passed, the resistor will not matter at all. I could say in this circuit, we would find the amount of charge that accumulates on the plates of the capacitor from Q equals CV. So I would say Q is equal to 0.1 times 10 to the minus 6, because the capacitance is given in microfarad, and we need to convert to farad. And the voltage drop across the capacitor will be the same as the voltage of the battery, 9 volts. And then I find the charge that accumulates on the plates of this capacitor will be 9 times 10 to the negative 7 coulombs. What if we considered a charging RC circuit and asked after a very long time has passed how much charge will be on the plates of this capacitor? Well, I could write out that equation. I could say Q is equal to C times E times 1 minus E to the negative T over RC. But we are asking after a very long time has passed. So that is essentially saying as t goes to infinity. And I could say as t goes to infinity, then e to the negative t over rc will become e to the negative infinity. And when I have a negative sign in an exponent, that basically means 1 over that quantity. So this term essentially becomes 1 over e to the infinity, which is going to be 0. Since this term is going to become 0, we essentially will be left with then at very late times, Q is equal to C times the voltage of the battery. But this is the same thing that we claimed right here. So I could say at very late times after the switch is placed in the horizontal position, the charge that accumulates on the plates of this capacitor will be 9 times 10 to the minus 7 coulombs. So far, we have not yet considered an RC circuit in this example problem. We began by asking the question, a very long time after the switch is placed in the horizontal position in this circuit, how much charge will accumulate on the plates of the capacitor? To answer that question, we claimed that you could imagine a circuit consisting of just a 9-volt battery and a 0.1 microfarad capacitor, and the amount of charge that accumulates on the plates of that capacitor will be the same as the amount of charge that accumulates on the plates of this capacitor at very late times. We then use Q equals CV to find the amount of charge that accumulates on the plates of that capacitor. I did demonstrate explicitly that at very late times, the e to the negative t over RC term in a charging RC circuit will be approximately 0, and I used that to justify our claim. Now we will place the switch in this circuit into the vertical position. When I place the switch in the vertical position, the circuit will look like this. And now the capacitor can discharge. Because the battery is not connected in a loop in our circuit, the battery has been effectively removed from the circuit. I could imagine that my circuit looks something like this now. To find the voltage across the resistor 8.4 milliseconds after the switch is placed in the vertical position, we will first find the voltage across the capacitor at that time. Because we are dealing with a discharging RC circuit, I could write V is equal to Q naught over C times e to the negative t over RC. Plugging numbers in, we find the voltage across the capacitor 8.4 milliseconds after the switch is placed in the vertical position to be 9 times 10 to the minus 7 divided by 0.1 times 10 to the minus 6 e raised to the negative 0.0084 divided by 30,000 times 0.1 times 10 to the minus 6. In plugging the numbers in this line here, the capacitance, the resistance, and the time were converted into farads, ohms, and seconds respectively from the units that are given. Also, instead of writing e raised to the negative exponent, I wrote exp with these brackets. The terms in brackets are understood to be in an exponent. This is a common notation that is often used, and the reason I used it here is to keep the work neater. So if I plug these numbers into a calculator, I find the voltage across the capacitor 8.4 milliseconds after the switch is placed in the vertical position to be 9 e to the negative 2.8, which is equal to 0.547. Because we have only 2 circuit elements in this circuit, whatever the voltage across the capacitor is, I expect this voltage across the resistor to be the same value. Opposite signs, but we won't worry about positive, negative signs for this example. Therefore, the voltage across the resistor at this time will be 0.547 volts.